Hello everyone, welcome to my channel. I am Niels van Niekerk from Vanik Developments. In this channel I will try to show you the various uses and aspects of the two-stroke and full-stroke simulation software EngMod2T and EngMod4T. In today's video specifically I want to show you how to create a two-stroke simulation model from scratch using Dat2T. There are several ways to create models. But the one I'm showing today is where you start from nothing. The other ways are copying existing models and renaming subsystems, etc. that I will show you in a future video. It is very frustrating once you start creating a model to find that you are missing critical information halfway through the process. To help you with this, Dat2T is created to prompt you and suggest values, so that you can actually create the full model without measuring anything other than knowing the bore and stroke values. The software uses the bore and stroke values to create these recommended values for you, and then you can afterwards measure the values that you do not know and edit the model before you actually start doing the simulation. As this is my very first YouTube video that I've created, I don't know what you want or what you like. If you leave comments below the video, I will see if I can improve in future. The other thing is, most people don't read help files, myself included. That's why I've actually started this channel. So sit back and don't read, but let me show you how to do these models from scratch. In today's video I want to show you how to use Dat2T to create a simulation model for EngMod2T from first principles. It is normally a daunting task for a first time user to create a model because there's a lot of info that needs to go into it. To help you, Dat2T actually fills in a lot of data based on default principles and will help you along. I prefer to create a model first and then go and measure the detail later on. The only detail you need right in the beginning that is very important is the bore and stroke and maybe the conrod length. The rest you can create or edit after you've created the model. The model I want to create today, I've just wrote down the basic principles, basic values for this model, and we can then create this model, and once it's complete you can go back and edit as is required. We start Dat2T by double clicking on the desktop icon. Before we enter, I first would like to show you a few things in the help file. If you click on the help button and then you open the topic Introduction to Dat2T and open the folder structure item, it shows you the folder structure used by the EngMod2T suite of programs. It shows you the working folder, what it's called and what the structure is inside the working folder, and then creates, once you start running a simulation, it also creates your project folder and it shows you what is inside the project folder for the different types of runs. Right at the bottom you will see there are also 3 files listed that very few people actually know about. It gives you the exhaust port, inlet port and transfer port area open against crank for at each RPM value. The next topic is the project layout. It describes the various engine subsystem and names of them and how many files are in each subsystem. The important thing is that it creates an error log also every time you use Dat2T. Dat2T is a dialog box based software, and sometimes people do not know what I talk about when I talk about a dialog or edit box or something like that. This is just a brief explanation of the Windows nomenclature. The final thing in the help file I want to highlight today is the error handling in Dat2T. Sometimes there's an error. It can be because of something you created, or it can be a mistake in the software. In any case, this explains how you report the error to me. At the bottom of this page there are 2 email addresses. You can use either of them and I will get the error. The important thing about the error log file is that every time you start Dat2T, it overwrites the previous version. It doesn't append or add on to it or anything. So it's important to, straight after an error has occurred and you exited Dat2T, to send me the error log file so that I can assist you in whatever went wrong. Okay, enough of that, let's start. The first thing we want to do is create a new project. We click on the new project button and type in the name of our project that we want to start. For today I'm just calling it new project, and you can see there it's filled in all the subsystem names as well with the name new project. We click on the accept button and the very first thing that will open is the engine data log. You will see the induction type is described here. We are today only running a naturally aspirated crankcase scavenge one. We are a spark ignition. We have a parallel bore. We do not have a step piston. It's a air cooled, water cooled. It's not an industrial engine. It's a single cylinder, is by nature an inline engine. Okay, we want to create an engine with 1 cylinder. We said the bore is 54, the stroke is 54. Immediately you will see that it falls in view the cylinder volume and engine volume, which is pretty much the same for a single cylinder. On a multi-cylinder it will differ. The conrod length that we want, the gudgeon pin offset, we have as 0 for this specific thing. We want to run a 14:1 compression ratio, and that's the geometric ratio, not the trap ratio. You can also specify the trap ratio. We have 0.8 millimeter squish clearance. We have a 50% squish ratio. Piston dome radius for this specific case is about 200. The deck height, we say that that it comes straight all the way to the top. We click the combustion. It will give us a warning there to tell us you first need to fill in the target RPM. We do that and we go back, and then it calculates all the various values for us. It shows us the maximum squish velocity of 39 meters a second. Our target brake mean effective pressure, we need to calculate that. Our target output is 45 horsepower, and that's a 13.02 brake mean effective pressure. We accept that. Exhaust pressure transducer, this is where you measure the temperature in the exhaust header. We'll make that 100. Inlet pressure transducer, we do 50, and we transfer one, we do it 25. I like to use 18 cycles in the beginning, and we want the throttle to be fully open. The crankcase compression ratio, normally when you measure it, the transfer volume is included in the ratio. In this specific engine, I have not measured it yet, but for a reed valve engine, a good starting point is 1.35 to 1. We are not going to, at this moment in time, do mechanical design and balancing, so we ignore that. It's an optional available feature. We click on accept. It will give us a warning message: the transport file is empty or incomplete. which is obvious. The reason why it gives you that is if we select the transfer volume included in the ratio, so it needs the transfer volume to calculate the final crankcase volume. Next, we automatically go to the exhaust port data dialog. We said that we want to use a single type but with auxiliary ports. For now we assume no power valve, and we looked at the values it's filled in here, and for a starting point this is fine, so we can click on save and display, and this is what it looks like with all the various values and things added there. Next, the transfer opens. It automatically opens for first time for 5 transfers. But if you want to change that, there's an option. You can also use this option to design your own transfer port layout. There's a button here where you can click it, but it'll tell you that the A port is very close to the exhaust port bottom. We can use it as is, which normally just means that it's a very narrow bridge, and we can calculate the values, and it gives us this. This layout is based on the Aprilia RSA porting layout as developed by Jan Til. We can display it and we see what it looks like. We decide we like this and we're going to accept it. And currently we use YAM14 as a scavenging model. In the help files there's a nice description of what the various scavenging models is. Pretty much the best scavenging you can get is the Aprilia RSW125 or the RSA125, pretty much the same thing. Average good is YAM14, we accept that. Gives us a layout of what our transfer ports look like, and we choose exit. Next, it opens the inlet port dialog. We want to use a case read for this case, and it opens it. We look it through the values. It's opened it for a typical 125 engine, and we save and accept it. It shows you the effective port diameter with the read valves fully open and the window area. It gives you the read frequencies. That also gives you the recommended read frequency. So what we see is we're probably a little bit stiff on the read pedal side, but we'll leave it for now. We accept that, and then the next dialog that opens is for a tuned pipe, or for the pipe types. There are various ones: open type, box pipe, silencer on an open pipe, silencer on a tuned pipe, T-pipe with open end, T-pipe with silencer, and it goes through and you have various options. For now we want to use a normal tuned pipe, and we click accept, and it opens a dialog box where you can fill in. In Dat2T, a tuned pipe consists of 2 pipes, and that is the basic pipe plus the tailpipe. The reason for that is where the tailpipe joins the main pipe, we can have various options there in a tuned pipe with different types of restrictions or venturis or things. The software will choose it depending on how you model it. We do not want to create or type in a pipe. We decide to use this facility, which is just what is available. We click on modern, which is your normal typical pipe that was developed in the late 70s and 80s. We select 650 because it's a fairly high performance engine that we're working with. We choose a value of 1.5 there, 0.6, 3.2 and 1, and we say display, we see, okay, the pipe is maybe a little bit fat, so we want to have it down to around 120, so we change that down to 3.1. Well, that looks a little bit better. The header angle, we want it to be a little bit less steep, so we change this to 1.6 and display. That's more like what we want, and we're quite happy with this pipe. We tell it return, accept, and now it's filled in all the data for you, and we can save and display. Next, the inlet system opens. We said we want to use an open-ended to atmosphere, no airbox or nothing, but we want a cylinder throttle, and we want the bell mouth end. We click OK. First off, let's look at this one. This is the pipe basically from the needle in the carburetor to the reed valve. We use the 38mm carburetor, and then it goes into the reed valve. I type in values that I remember, but it might be wrong. We'll see now what it looks like when we click on display. Okay, it looks reasonable, except for the first one. Let's increase this to 55. Display. That looks more like a bell mouth, maybe not a little bit more. Okay, that looks like what I wanted it to look like. Save and display. That's now we've created our inlet system. Next we get to the combustion and ignition. We said we want to use avgas, and we want to use a burn rate prescribed model. There's no nitromethane. As a very first starting point, we can use this utility, create an initial ignition curve. It warns you that this is just a starting point, and no guarantee that it's the best curve. We click OK, and it's generated the mixture and the timing values for us, and also the vibe or Weber values. We can look at what it's created. This is the timing curve, is the red one. The green one is the timing curve minus the delay, and the black line is the air fuel ratio. This is the vibe values. Okay, we say save and exit, and then the final one we need to complete is the temperatures that we use in the engine. We said it's a water-cooled engine with air-cooled crankcase. We click accept, and it fills it in for us, except that we don't want to use the exhaust wall temperature as a constant. We would rather have it as a function of RPM, and we click that button, and it will use these values as a default. You can of course change it if you have better information, and using these values, this specific one will be ignored. We are at sea level and at 20 degrees Celsius, so that's all very well. We click accept and save, and there we've created our full model. Now there are another thing we need to do: pipe, duct and passage check. This just verifies that there's no anomaly or anything that will cause long run times or issues. we can see that everything looks fine. And finally we look at the specific time area. It just warns that the port width might be bigger than the bore circumference, but we know it's not. It's just a final check, and it gives us the specific time areas. We see that on the main exhaust port, which is not super critical, we're slightly bigger. On the auxiliary exhaust port plus the main exhaust port blowdown, we're quite a bit bigger than required, so we might have a problem there. Our transfer ports are just making it, and the specific time areas for the reed block and for the reed petal opening is ballpark also okay, so we say exit, and then we say exit. We have now saved this value. All the data is now saved, and the next step will be to run this in Engmod 2T, run a simulation, and then see how it performs, and then go back and modify the data or measure the engine and get better information and input that into the program. I think that's about enough for today.